Hello viewers, welcome to CAE for you. Sometime back, we posted a video explaining simulation of heart of retouch process, in which we discussed about setting up favorable residual stress in a pressure vessel so that the load capacity of the pressure vessel could be improved. Such process is known to have significant improvement in life extension of the load bearing member. More specifically, when the improvement has to be effected without increasing the size or choosing high strength materials, eventually leading to cost effective product design. While the benefit is evident, such complex simulation are tedious and often require elastic plastic material modeling. However, it is encouraging to see if such concepts can be extended to a torsionally loaded member. So in this video, we will see if such benefits can be obtained in a torsionally loaded member. The typical application is torsional spring, which are often used in on-road and off-road vehicles. While searching for any previous work in this area, we found an interesting paper. We were wondering if this simulation can be done using open source tools. Interestingly, the simulation in the literature was performed using Abaqus. We are hopeful that this will be another case to demonstrate the capability of open source FEA tools in performing industry quality simulations. Just to explain the model, the geometry is a simple cylindrical rod characterized by its length L and radius R. We note that though the behavior is expected to be two-dimensional, it is not possible to use 2D analysis systems within the software and hence necessitates 3D geometry for simulation. The cylinder is fixed at one end and twisting load is applied at the other end, which we will call as the free end. While twisting load is typically in the form of torque, angular displacement was found as a convenient load. This is because the torque is typically unknown upfront the simulation, as the initial loading is convenient to specify in angle of rotation. Further, angular displacement is a better form of loading from convergence standpoint too. Once solved with the angular displacement, it is possible to obtain equivalent torque and subsequently apply the torque load. Hence, the simulation was planned in sequence, while the first load case would be displacement controlled and the next would be torque controlled. So the first load case is controlled by subjecting the free end to an angular displacement theta. This is again to make the load condition compatible with the software. However, in the literature, the angular displacement from fixed end was provided, and let us call this as gamma. Since we need theta, it is necessary to convert gamma into equivalent theta. It can be calculated using the simple relationship r theta is equal to gamma times length, that is L, and hence theta is equal to gamma times L divided by R. Now we have obtained a loading condition for the simulation. In order to ensure the solution to be comparable with literature, the material properties were extracted from the material curve specified in the paper. The material constants were also considered to be the same values. It is important to mention that the plastic portion of the material curve is obtained by digitizing the curve in the literature and further processing to obtain the plastic strain. The data is adjusted to account for small calibration errors. We have used the default material hardening model, while it can be extended to other models if necessary. The simulation workflow is as usual. We created the geometry using FreeCAD consisting of the rod with the dimensions as specified in the reference. We also created the slicing feature to enable structured hex mesh. We did the meshing using Salome. A modest refinement was made, balancing accuracy and resource utilization. We did the solving and post-processing in Calculix. As stated earlier, the entire simulation can be essentially divided into two sequential load cases. The first load case is the displacement control load corresponding to the so-called presetting condition. From the literature, The corresponding condition is to ensure gamma to be 0.043. Based on the dimensions, the theta value corresponds to 0.258 radians. The loading will stress the component beyond yield, and in the software it is possible to obtain the corresponding torque for subsequent analysis. The torque value corresponds to 278.24 Newton meter, while the result obtained using abacus is reported in the paper was 284.2 Newton meters. This is about 2% difference. While we will compare all the results later, this comparison is essential to proceed for next step. Now, this torque is applied and released in the second simulation. We notice that the residual strain is 0.023 while the reported value is 0.024. We see the results are reasonably close, that is, they are within 5% difference. Let us compare the contour plot of the results from the reference versus the results obtained using Calculix. We notice that the pattern matches very well for both presetting and residual load conditions. To take a deeper look, we measure the residual stress across the radius and compare against the published values. To our surprise, the result compare very well with the literature even quantitatively. Though a further refinement and mesh realignment could produce a more smoother curve. Nevertheless, it is interesting to note that Calculix results of 298 megapascal residual stress is even more closer to the experimental value of 335 megapascal when measured under 5 micrometers beneath the surface versus 287 megapascal reported in the paper. Let us look into the summary of various output values between reference and Calculix. We could make out that the results agree very well. It indicates that the modeling approach is consistent and we can expect good quality results. While performing this simulation, we also observe that the result obtained can be further useful to calculate the stress ranges more easily. Since the residual stress will be constant for a given presetting and the subsequent loads would be typically within the elastic range, a simple calculation using the strength equation can be calculated to assess the favorable stress range. This is possible because the resultant stress is algebraic combination of the residual stress and the elastic stress. Note that if the applied load crosses elastic limits, superimposition would not work. We found this method is advantageous because finding the best possible combination is iterative and FEA can be costly for larger models. It further becomes more complex in the presence of stress rises like splines or steps in the rod. If you are interested, you can watch our previous video to see how stress concentration is modeled using FEA. Coming back, to verify if superimposition works as expected, the simulation was extended to reload the model from the residual stress condition. A torque value of 152.2 Newton meter was selected, corresponding to the maximum shear stress of 775 megapascal. As shown in the graph, the results are identical, which confirms this approach can be reliably used within the previously stated limits. Lastly, we would like to highlight on the resources used. In a 4-core machine, it took 407.5 seconds for solving. This is about half core hour runtime, which is a resource efficient approach for the accuracy level. Yet again, Calculix proves to be an excellent open source software in simulating complex physical problems. Thank you for watching.